We're going to continue looking at derivative applications today. In particular, we're going to look at some ideas about rate of change. Let's start out with a familiar graph. So on your paper, take a second to sketch this very rough sketch that we've looked at before when we just started looking about derivatives. So something that kind of curves like this. It doesn't have to be exactly the same, but a rough curve. One of the things that we talked about in the past, particularly when we were defining derivatives, is we imagined that we could have a point right here and another point up here, and if we connected those two red dots, we would have a line segment. This line segment has a special name. It's called a secant line. So a secant line connects 2 points on the curve. And then what we talked about was taking this point over here when we defined the derivative, and we slid it super close to this point. We let the limit of the function happen as h approaches 0. And then what we ended up finding is information about the tangent line. So remember, a tangent line occurs like this. So you have in a neighborhood, in sort of a small neighborhood of your function, it touches and rests upon the curve. Okay, and this guy is our tangent line. Now it turns out that in our course, we're interested in the slopes of both the secant line and the tangent line. So that's what we're going to look at today. So let's make a list over here. We've got the slope of the secant line. And then the other thing that we're interested in is the slope of the tangent line. Now there are some calculus buzzwords that refer to each of these, and so we want to be familiar with those. If somebody's talking with you about the slope of the secant line, then words that they might use include finding the average rate of change. So the average rate of change. In contrast, if somebody's talking to you about the slope of the tangent line, then they might use the phrase instantaneous rate of change. Okay, so slope of the secant, the key word there is the average rate of change. Slope of the tangent, instantaneous rate of change. It turns out that slope and rate of change can actually be used synonymously, so that's why each of these parts refer to a rate of change. Okay. Now, one of the things we want to be able to do is to find the actual value, the numerical value for the slope of the secant, or the average rate of change, and also for the slope of a tangent line. And let's take a note so that we can refer to this later on. If somebody asks you to find the slope of the secant line of f of x, I'm going to put it m for slope, and then a little SEC down there. So the slope of the secant of f of x. And your reader is going to have to tell you what the interval is. So what do we care about for the interval of these? So the slope of the secant on some interval will go from a to b. If you look back at our picture, a might be this point right here, first red dot, and b might be the x-coordinate of that second dot right there. If you want to find the slope of the secant of f of x on a to b, then that's going to be equal to our regular old delta y over delta x. So what you would have done back in early high school, maybe even middle school. So we're going to take the y value, f of b, we're going to subtract off the y value at a, f of a, and we're going to do that over b minus a. That formula will give us the slope of the secant line. In contrast, if somebody asks you for the slope of the tangent line over here, we know that instantaneous rate of change refers to the tangent slope. We also know that the slope of the tangent is another word for derivative. So if somebody asks you for the slope of the tangent line, then your work is going to be a little bit different. Here's how we might set it up. The slope m of the tangent line of f of x. Typically for instantaneous rate of change, we have the tangent line at just one point. Check out our picture there. So we would say, instead of an interval, like we said over here, we're going to say the slope of the tangent of f of x at x equals a particular number, like at x equals a. And then to find that, what we would do is we would take the derivative of f of x, f prime of, and then we would evaluate that derivative at the given coordinate, at a. Okay, so as a recap, the average rate of change, we get to use regular old slope formula. Instantaneous rate of change, we're going to use our derivatives. What we'd like to do next is look at a couple of examples, so see how this actually plays out. So example 1 gives us a function. I've got a nice product right here, and it asks us to find the average rate of change of this function. Okay. Now, average rate of change, if you look back in your notes a little bit, average rate of change is just delta y over delta x of the original function, f of x. So in order to get started, I'm going to look at my interval. Here's my a value. Here's my b value. And probably the most prudent thing to do is to go ahead and get my xy pairs. So for my first value, I have -1 as my x-coordinate. In a second, I'm going to find the y-coordinate. And over here, I have this 2 is my x-coordinate right here. And we're going to need to find its y-coordinate, which we'll fill in just a second. To find these y-coordinates, then all we're going to have to do is take the x values and plug them into our f of x function. Here we go. So f of -1 is going to be equal to -1 to the 4th plus 3 times 2, -1 cubed, minus 1. Let's simplify this. 1 plus 3, -2 minus 1. Ended up with 4 times a -3. Looks like our y value is -12. So let's write it up here, -12. Let's play the same game over here for the 2. So let's take this 2, we're going to substitute it into our original f function so I can get that missing y value. So I've got 2 to the 4th plus 3 times 2 times 2 to the 3rd minus 1. 2, 4, 8, 16 plus 3. 16 minus 1. 19 times 15. Which gives us 285. A whopping big y value, but that's okay. Now we've gotten things set up, so we've found our 2 coordinates that we're going to use. Now we just have to use our formula that we just wrote down. The slope of, separate this off, the slope of the secant is going to equal my change in y's, so I'm going to scoop up my y values and subtract them, 285 minus -12 over my change in x, 2 minus -1. Technically you could stop there. It kind of gives me the heebie-jeebies to stop there, but you could. Got a 3 on the bottom, plus change. Looks like 297 or so. So apparently the slope of the secant is super steep, 297 over 3. Now let's take a look at an instantaneous rate of change problem. So this is example 1b. We're going to keep our exact same function right here, and this time it's going to ask us for the instantaneous rate of change. I know that instantaneous rate of change is code for slope of the tangent, which is code for derivative. I also have a clue because they gave me a single x value as opposed to an interval. And I know that if I need to find the instantaneous rate of change, we're going to need the derivative. So let's start out with the derivative. Now globally, when I look at this problem right here, I see that I have a big old product rule happening with some little chain rules happening inside. So let's start with a copy of the first, x to the 4th plus 3, times the derivative of the second part right here, which is 6x squared. First time plus. Now I'm going to take the derivative of the first part, 4x cubed, times a copy of the second part. Now that we've found our derivative, it's going to be pretty easy to find this instantaneous rate of change. All we need to do is evaluate the derivative at x equals 3. So let's find f prime of 3. We're going to sub in this mess, 3 to the 4th plus 3 times 6, 3 squared plus 4 times 3 cubed, 2 times 3 cubed, minus 1. At this moment I think AP that I don't have to simplify, and I can stop right here. If you are dissatisfied stopping here, then feel free to type all that in your graphics calculator and find a single numerical answer. As you're working these problems, it's important that you look carefully at the wording and the information they give you. So be on the lookout for instantaneous and receiving just a point, in contrast to receiving a problem that has average and an interval.